Hi, welcome back to my channel. My name is Gina. In this video, we're going to learn how to sketch a function without knowing how this function is supposed to look like. So I summarize it into 8 steps that can help you to gather all the information you need to sketch a function. The first one is to get a consideration of domain, if the domain is all real number or if it has a vertical asymptote. So the second step is to find the vertical asymptote. So we'll take the left-sided and right-sided limits around the asymptote to find whether the function will go to positive or negative infinity. And the third step to find the horizontal asymptote. So we take the limit as x approaches infinity and as x approaches negative infinity. And that will tell us whether the function will approach to a number at the infinities. And then the fourth step, we'll find the y-intercept, which means when x equals to 0. And then the fifth step is to find the x-intercept, which means when the y equals to 0. So we'll solve the function. And then the sixth step, we'll set up a sign table for the first derivative and the second derivative. And the interval where the first derivative is positive, it means the function is increasing. And on the interval where the first derivative is negative, it means the function is decreasing. And for the second derivative, if it's positive, it means the function is concave up. And if second derivative is negative, it means the function is concave down. There's more explanation on the increasing, decreasing, concave up, and concave down in my online course. And I'll put the link down below and you can enroll today. And then the seventh step, we'll set up a table for y-intercept, x-intercept, and local maximum and minimum, and inflection point. And then lastly, we'll sketch. Now let's look at an example. Let's sketch the function line of x over x using the 8 steps that I just mentioned. So first, we'll get a consideration of the domain. For the log function line of x, we know that x must be greater than 0. And the function is a fractional form, so the denominator can never be 0. So x cannot be 0. So let's put these two information together and we get the domain must be x is greater than 0. Then the second step, let's find the vertical asymptote. And since the domain is when x is positive, so we only need to take the right-sided limit. So as x approaches 0 from the right, of line of x over x. And if we use the cheating rule, we'll get negative infinity for our line of x, and the denominator would be a really small positive number. So this limit will go to negative infinity. And then the third step, let's find whether the function has a horizontal asymptote. So we'll need to find the limit as x approaches infinities. If we use the cheating rule, we'll get positive infinity over positive infinity. So let's use the L'Hopital's rule. Limit as x approaches infinity, derivative of ln is 1 over x. And derivative of x is 1. So we are left with limit as x approaches infinity of 1 over x. Now let's use the cheating rule again. 1 over a really large number equals to 0. And this would be a positive number. And since the domain of the function is x greater than 0, so we do not need to find the limit as x approaches negative infinity, since that's outside of the domain. And then the fourth step, the y-intercept, meaning when x equals to 0. However, the domain of the function is x greater than 0. So x equals to 0 is outside of the domain. So this function has no y-intercept. Now let's look at the fifth step, x-intercept. So when y equals to 0. So we need to solve line of x over x equals to 0. And since the denominator can never be 0, so the only way to make this function equals to 0 is when line of x equals to 0. And this equation is equivalent to e to the power of 0 equals to x. And e to the power of 0 is 1. So the y-intercept is when x equals to 1. Or if we put that in coordinates, we have 1 for x and y is 0. And then the sixth step, we need to find the first derivative and the second derivative for the function ln of x over x. Let's find the first derivative. Here we have a function of x in the numerator and a function of x in the denominator. So we need to use the quotient rule. So this equals to derivative of numerator times denominator minus the numerator ln of x times derivative of the denominator, which is 1, over the denominator square, so x squared, which equals to 1 minus ln of x over x squared. And we want to solve for the first derivative since we want to set up a sign table. So let's find the critical values. 1 minus ln of x equals to 0, which means when ln of x equals to 1. And that is when x equals to the constant e. So at x equals to e, the derivative function equals to 0. And the first derivative does not exist at x equals to 0. However, f of 0 is undefined. So x equals to 0 is not a critical value. So the only critical value for the function is x equals to e. Now let's see the second derivative. So we take the derivative again from the first derivative. The first derivative was 1 minus ln of x over x squared. So again, we need to use the quotient rule. So from here we get negative 1 over x times x squared minus 1 minus ln of x times 2x over x to the power of 4. And this equals to negative 1 minus 2 times 1 minus ln of x over x cubed. And we want to solve for the second derivative, so we set this equals to 0. So the inflection point is when negative 1 minus 2 plus 2 ln of x equals to 0. And this equals to 2 times ln of x equals to 3, which is equivalent to ln of x equals to 3 over 2. So when x equals to e to the power of 3 over 2. Now let's set up the sign table. So we had x equals to e, that is the critical value. And when x equals to e to the power of 3 over 2, and that is the inflection point. Let's start with the first derivative. So at the critical point, the first derivative is 0. Now we can substitute a number in each interval to find the sign. For example, we can substitute 1 in the first derivative, which is 1 minus ln of 1 over 1 squared. And ln of 1 is 0. So this equals to 1, which is positive. So over this interval, the first derivative is positive. And you can do the same thing with the interval when x is greater than e, and you'll find that the first derivative is negative when x is greater than e. Now let's look at the second derivative. So the second derivative equals to 0 when x equals to e to the power of 3 over 2. So we need to find the sign for second derivative when x is smaller than e to the power of 3 over 2 and when x is greater than e to the power of 3 over 2. So again, we can substitute any number within each interval to find the sign. For example, I can substitute when x equals to e. In the second derivative, we found that it was negative 3 plus 2 ln x over x cubed. And when we substitute x by e, we'll get negative 3 plus 2 times ln of e, and ln of e equals to 1 over e cubed. And this is negative. So over the interval when x is smaller than e to the power of 3 over 2, the second derivative is negative. And similarly, you can substitute any number for the other interval, and you'll find that the second derivative is positive over this interval. So what does that tell us on the graph? When the first derivative is positive, it means the function is increasing. And when the second derivative is negative, it means the function is concave down. So we combine these two, we get that the function will look like this. And then for the interval when x is between e to the power of 3 over 2, we have the function is decreasing and it is concave down. So we put that together, the function will look like this. In the last interval, we have the function is decreasing and the function is concave up. So the function will look like this part of the concave up. Now, seventh step. Let's find the coordinate of some important points. For example, from the fourth step, we found the x-intercept when y equals to 0 is 1. And from the sine table from the sixth step, we also found that when x equals to e, there's a local maximum. Now let's find the y-coordinate when x equals to e. So the function was line of x over x. And when we substitute x by e, we'll get 1 over e. So the local maximum occurs at e and 1 over e. Now let's put everything together and let's sketch the graph. So the function has x-intercept at 1, 0. And it has local maximum at e and 1 over e. And we also found that it has vertical asymptote at x equals to 0, and the right-sided limit is negative infinity. So the function will start from negative infinity and you'll pass through the x-intercept. Since we know that over this interval, the function is concave down until x equals to e. And at x equals to e, we have a horizontal tangent line because the first derivative equals to 0. And then we have an inflection point at x equals to e to the power of 3 over 2. So when x is between e to the power of 3 over 2, we have concave down. However, when x is greater than e to the power of 3 over 2, we have concave down and the function is decreasing. And we also found that the function has a horizontal asymptote at y equals to 0. So the function will never cross x-axis. So that is the end of the video. If you want more examples or if you want to learn more, I have an online course on Calculus 1 and I'll put the link down below. You can enroll today and become my student. I hope this video helps you and I'll see you in the next video.